most limit problems don't work out as easy as this, though. Typically, when you plug in x equals the number into your function, you'll usually either get something of the form 0 on top and 0 on the bottom. This is definitely not 1. Or you get something non-zero over 0. We're going to work on some of the cases where you have 0 over 0. And again, these aren't hard and fast rules, but they are general rules. So if you have something of the form 0 over 0, typically your solution will end up being a finite number, at least for a lot of the examples that you'll encounter. And there's probably 4 good common tricks to always use to approach these problems. One is you can try to factor and cancel. If there's a fraction floating around, try to get common denominators and simplify it down. If there's something to multiply out, try to expand it and multiply it out and see if that helps. If there's a radical involved, try multiplying by the conjugate. And then there's the others. There's, kind of problems that don't fit into one of these molds, and you may have to be a little creative on them. So take a look at one of the other videos. I'm definitely going to do an example of all of these. And then we'll come back to the limits at infinity and also what we do on the non-zero over 0 cases. Again, though, limits are frustrating, so if they're tripping you up, you're definitely in good company. I think everybody tends to have a little bit of an issue with them at the beginning. Okay, now we're going to start talking about limits here a little bit. So limits are one of those things, they're just not completely mechanical like we would like them to be. So you have to know some different tricks on how to deal with them. So to begin with, let's start off with this equation, y equals x minus 4. The basic idea with a limit, we can use an example to explain as follows. So suppose we take numbers close to 5. 5.1, 5.01, 5.001, or say 4.9, 4.99, 4.999. Well, if you did the arithmetic with those numbers, in each case you get out a number relatively close to the number 1. And that's basically the fundamental idea of a limit. We're putting in numbers close to a specific number, and we're just trying to see what numbers we would get out of our formula. The notation for this is we write, in this case, we write the limit as x approaches 5. I'm taking x coordinates close to 5, and if I plug them into the formula, I get numbers close to 1. Now, I think this notation is a little deceiving because here there's a little arrow that says as we take numbers close to 5, it says the limit equals 1. And it's a little deceiving. What you should really think is as x gets close to 5, x minus 4 is getting close to the number 1. But the notation is what it is, and they use an equal sign. But I think this is something that confuses people. They see this equality, and they think, hey, it's definitely equal. In general, we write the limit as x approaches a, so we're taking x coordinates close to something, we're plugging them into our function, and we get some number out. The number out that we get is known as the limit of the function. Okay, so there's definitely a whole lot of different ways that you deal with limits. So to start off with, there's a couple different cases. So we have the limit for x approaches a finite number, like in our last case, or x can be going off to positive or negative infinity. And all that means is we're putting in either very, very large positive numbers into our formula, we're trying to figure out what we get out, or we're putting large negative numbers into our formula, and we're trying to see what types of numbers we get out. Still with this case at the beginning. Okay? So there's a couple things that can happen. The basic idea on how you try to do a limit is you plug and chug. For example, in our last example, notice that you simply plug in x equals 5. Well, 5 minus 4 is 1, and that's your solution. Typically, most limit problems don't work out as easy as this, though. Typically, when you plug in x equals the number into your function, you'll usually either get something of the form 0 on top and 0 on the bottom. This is definitely not 1. Or you get something non-zero over 0. We're going to work on some of the cases where you have 0 over 0. And again, these aren't hard and fast rules, but they are general rules. So if you have something of the form 0 over 0, typically your solution will end up being a finite number, at least for a lot of the examples that you'll encounter. And there's probably 4 good common tricks to always use to approach these problems. One is you can try to factor and cancel. If there's a fraction floating around, try to get common denominators and simplify it down. If there's something to multiply out, try to expand it and multiply it out and see if that helps. If there's a radical involved, try multiplying by the conjugate. And then there's the others. There's, kind of problems that don't fit into one of these molds, and you may have to be a little creative on them. So take a look at one of the other videos. I'm definitely going to do an example of all of these. And then we'll come back to the limits at infinity and also what we do on the non-zero over 0 cases. The limits are frustrating, so if they're tripping you up, you're definitely in good company. I think everybody tends to have a little bit of an issue with them at the beginning. Right, in this video, I just want to do some problems, some basic problems related to limits and graphs. Basically, being able to look at a graph and evaluate a limit. I think it's, limits are something you do a lot in calculus, and I think to do a lot of limits, I think about graphs and functions. So it's kind of a fundamental idea. So nothing hopefully too heavy. This is stuff that certainly can be confusing the first time, or the second time, or the third time you see it. But this is the basic idea. So if you look at our graph here, y equals f of x, you notice there's a little break in it at the x coordinate of 3. There's a little hole, so there's a point of discontinuity, and that's fine. Nothing going on there. One little observation here, so just to take on a point in particular, notice if you take an x coordinate that gets closer and closer, say, to x equals 3. If we take an x value that gets closer and closer to 3, whether we kind of come from the left side of 3, that means using smaller values, obviously, or from the right side of 3, and that means we're using, well, values larger than 3. If you think about on the corresponding graph, what are the y values getting closer to for those x values? Well, to me, it looks like as x gets closer and closer and closer to 3, the y values on the graph are simply getting closer and closer to 2. So, no big deal. So I went ahead and wrote that down. Basically, it says, again, if x gets closer to 3, f of x, or equivalently the y values, does get closer to the number 2. Notice it's even undefined at 2 because of the open circle. Still, as x gets closer to 3, the y values numerically get closer to 2. We write that as the following. We say the limit as x approaches 3 of the function f of x equals 2. See this notation, all it says is, you've got some graph, y equals f of x. If you plug in stuff close to 3, it says, hey, the y values get close to 2. We write an equal sign, I think that's a little misleading because it never actually equals 2. But it gets as close to it as you want, and that's the idea. So, put a couple problems here with a graph, and we'll just try to answer some of these. Okay, so notice my little graph here. It's got a break at -2. It's got a vertical asymptote at x equals 2. There's another little break here at x equals 4. So the first question here just says, what is f of 0? Well, all that means is, right, you're just plugging in x equals 0. What's the corresponding y value? Well, in this case, f of 0, which is equal to the y value of 2. Hopefully you can see that. This limit question, it says, okay, what's the limit as x approaches 0 of f of x? So again, that to me says, as x gets closer to 0, what do the y values get closer to? Well, here's x equals 0, so I just find the corresponding graph, and again I think, well, as x gets closer and closer to 0 on the graph, the y values are getting closer and closer to the number 2, no matter which side you come from. So, in this case, we'll say the limit as x approaches 0 of f of x is also 2. And this is something that's important. You'll see this in another part of the problem here. This has to be a unique number. If not, we simply say the limit doesn't exist. Okay, so what if we ask what's f of -2? Well, that simply says if you plug -2 into the function, what do you get out? What's the corresponding y value? Well, this simply says if you plug -2 in, since our dot is up here at 5, it says if you plug -2 in, well, you get 5 out, okay? Again, that simply means if we take x coordinates close to -2, if we take x coordinates close to -2, what are the corresponding y values getting closer and closer to? And in this case, it looks like if x gets closer and closer to -2, to me, the y values are getting closer and closer to 1. So in this case, I would say the limit as x approaches -2 is just 1. So again, this is important. It doesn't actually matter what happens at -2. It just happens, the only thing that's important is what happens when you get close to -2. If you get close to -2, the y values get close to 1, okay? So, let's see a couple more here. Suppose we do the limit as x approaches +2 of our function f of x. Well, in this case, as x approaches 2, the y values on the graph, well, they just get bigger and bigger and bigger and bigger. And it doesn't matter whether you come from the left or the right. They just get larger, larger, and larger. Sometimes if they go to infinity, people will say it does not exist. In this case, I would actually write that. I would say, well, the limit goes to positive infinity. And what that means is, again, it says the graph is spiking off. Okay? Let's see, just a few more here. F of 4, that says if you plug 4 in, what y value do you get out? Well, if you plug 4 in, it looks like you're getting out the y value of 1. And just a couple more questions here. Let's do, suppose we ask ourselves what's the limit as x approaches 4. I left this one out. Well, notice in this case, it kind of depends, because if you take, x coordinates that are close to 4 but smaller than 4, well, those y values get closer and closer to 1, right? So x values to the left of 4, that means I'm going to be on the graph just a little bit to the left of 4, and the y values get closer to 1. Well, but if you do it, for x values just a little bit bigger than 4, well, now you're on the upper portion of the graph, and then it says the y values get closer and closer to, I don't know, we'll pretend it's lining up here at +4. So you can't say two numbers. You can't say it's like 1 and 4, In this case, if the limits aren't the same from opposite sides, and we have a better way of saying this, we simply say that the limit does not exist in that case. So to me, basically it says if there's a break or a jump in the graph, the limit doesn't exist. However, we can talk about limits from the left and limits from the right on graphs. This will be the last two problems here. What we'll do is we'll write the limit as x approaches 4, and then we've got a little positive sign. What that means is from the right of the number 4. And if we're to the right of the number 4, that means we're using numbers, well,